Hey all, welcome back to the lab. In this video, we are going to go into my solution for Advent of Code 2024, Day 5, using F#. So as a reminder, Hymenians members do get full access to all the project files that I'm going to demo today, so you can get clone and run it yourself, but we will be going over all of the solution code, and it's in the blog post, so you can just copy and paste it if that's more your bag. All right, so let's start off with Day 5, Part 1. So as usual, the prompt is here, but I can't show it. But if you want to read it, you can go to their website and look at it. And instead, we'll just go directly into my summary of this, my takeaways, and kind of what I coded off of. And so basically, we are given some page ordering rules in the form of X bar Y. And basically what this means is that if X and Y are in this list, then X must come before Y. So this says X must strictly come before Y. And as we'll use later, this means that Y must come after X. So that's the first part of the input. The next part of the input is pages in each batch, I guess we could say. And those come after in the form of, X, comma, Y, comma, Z, but there could be like many more of those. So ... And the ask here is basically, can you find the pages in the correct order? And then to prove that you can, you need to sum the middle element of the page batches that are in the correct order, thus proving that you've done it. And so there's a few sub-problems here. Really the most pressing one is like, how do we even tell if some pages are in the right order or not? And basically this is a solution I came up with, and it seems to work in like O of n times m time. And basically what we're doing is we're gonna, have the jumbled string, or, I guess just the list of pages, and then we're gonna iterate over it, and we're gonna keep a set of numbers that are to the left of us. And then for each page, we're going to look up the number, like the current page number, to the vowels that must be after it. And then we basically are just going to be like, are any of these numbers that must be after our current page in the set that we've already seen? Because that means they've come before, but we know it must come after. And if it's there, then it's a bad page, it's invalid. And so we can say that this is bad. But if we iterate over everything, and we don't see any of these rule breaks, then we're like, oh, okay, it's fine. So that's what we're doing. And it seems overly simplistic, but it does seem to work here. And so that's what we went with. And so basically the solution for this overall is to pre-process the input, check if each is in order, and then sum the middle elements. And I got something like O of 2n plus n times m squared, where m is like the number of pages in a batch, with 2n extra memory. And so we end up processing the input into lists of page lists. We process the input into a lookup of, X to all of its Y rules. So for every page, what are all the rules for pages that must come after it? Then we create a little helper function is page in order, which, does the algorithm that I mentioned above. And then we're just going to iterate over every page list, check is the page in order, keep only the ones in order, and then return the sum of the middle string. So that's a lot of the pseudocode. And here's the code here in F# if you want to copy and paste it, but we'll also open this up in my editor so we can get some syntax highlighting. Okay, so here we are, and I basically have a type for the Day 5 input because I was like, I want to make sure that we are creating this fine, and this came in useful because for the second part I actually had to change what this was. But basically the input, we want to process it into some structured data, and so we're going to say, so number to the values after it, so this is the page number to all values that must come after it based on the rules. This is going to be a dict of int to int list so that we can do fast lookups. This probably should have been a set, but I went with the list for here. And then the pages is an int list, so it's a list of int lists. So we're reading the input, and basically we get all lines here with my utility function. And then we are trying to find all rules where it says X to the vowels after it, so X to all Ys. So basically we're just going to loop over all seeks, or all lines, and we're only going to take the ones with this bar because we know this indicates that it's a page ordering thing. Then we're going to split these ones so that we get X, Y. Then we're going to turn this into a tuple so that we can access it easier. Then we're going to group these tuples by X, so this will give us, the page number to all of the groups, all of the rule groups, I guess, that have that X. And then we simply flatten the Ys from those groups and then make it so that we have a tuple of X to just the Ys here, and then we turn that into a dict. So that's how we're getting X to the list of Ys. A little complicated. There's probably a more concise way to do this, but this is what we did. Then we're going to get all pages, so we have to read in all of the lines. We're going to filter them to only the ones with commas because we know those always have commas in them. We're going to split on commas so that we have each of the pages. And then we're going to map each of these to turn them into ints. And then we're going to turn that into a list so that it's already materialized. And then we are going to turn this into a list as well so we get an int list. And finally, we're going to return these here. So we get structured input. We make sure that it's the type we actually expect. And we can start processing on this. So that's our read input. And I guess I should look at the solve part one first so we know what this is happening. But so we call solve part one, we read our input in, so it gives us all lines. And this is actually the structured input here. And then we are creating a queried function here of is in order. So is page in order requires, all the rules. And so I'm just querying this so I don't have to pass this in every time. And then what we're going to do is basically for each of the pages on the input, so each of these int lists, we are going to choose the ones that are in order based on our calculation, which we'll dive into in a second. And then this means that by the time we get here, we've only filtered to the ones that are in order. And then so we're just going to take the middle element of this, and then we're going to sum those. And so that's how we're doing this. And then the magic is really happening in is in order, which is actually is page in order. And so we'll dive into this as well. And so we need our rule book. And so this is, page to pages that must come after it. These are our rules. And then this is the pages in the current batch. And so we're going to pre-populate pages to left here with the first element of pages because, why would we start at 0? There's nothing to the left. We didn't necessarily have to do this, but thought it was cleaner. And then we're going to start this off as is valid because I didn't know of a way to do early returns out of a loop. And so I just wanted to avoid this entirely. And so this will hold whether the current page is valid or not, or the current batch of pages is valid or not based on our rules. Then we are going to iterate from I equals 1, so the second element to the end of the thing. We're going to pull out the current page, and then basically what we're trying to say is if the current page has rules, so if it doesn't have rules, we don't care, but if it does have rules, then let's see if any of those rules for things that must come after it have actually come before it, in which case it's bad. So we say pages in the wrong order if pages that must come later of it, if for any of these our pages to left set contains that page. Then if this is in the wrong order, then we're just going to set is valid to false because this is no longer valid. And really we could early return here, but I didn't. And then what we're going to do is we're going to iterate, so pages to left equals to pages to left dot add. So we're adding this to the set, but this returns a new set. So we actually have to mutate over this to make sure that it's there. And then at the end, we would just return as valid. So a little bit wasteful. We probably should have done an early return here, but that's okay. And we iterate over all the things and we get the right answer according to advent of code. And just to prove this to you, we have the 2 stars here for 5. So we did get the right answer. Okay, so that's part 1. Now we go into part 2. So again, the prompt's here, but we'll just go over my summary. And so we're given the same inputs as above, right? But now the ask is to find only the incorrect page orders or incorrect page batches, I guess. And then we need to put them in order. And then to prove that we've done that, we sum up the middle pages of the in order version. Now the subproblem here is how do we reorder? And there's several solutions to this, most of them bad. So the first one is, can we just randomize this till we find one? And there's a few problems with this. 1, we just might get unlucky and never find it. 2, obviously this is pretty inefficient. The second one was, let's try all combos of ordering. So, we would simply just find all different combinations so that at least we know we've tried everything, exhaustive search, so that, we don't get into this endless thing. We know we will find it if it exists. And then we can just reuse our is in order function that we made earlier. And so I was thinking that this would be O of m squared times m, because I was thinking of combinations, and I was oh, this is brute force, it's kind of slow. Turns out this is actually closer to m factorial, which is much more complicated, as we'll talk about in a second. And so these are the first 2 I started with because these are the ones I saw memes on Reddit, but I didn't realize they were memes because, this is actually probably not possible. And then if this is too slow, it's probably possible to do some sort of topological sort based on the rules, and then you sort with the graph. All right, so let's talk about some of these. I started off with the brute force solution because I was I already have these things. It's probably not going to matter this much. The most we have is 5 elements or something on the inputs. And this does work for the testing and debug inputs that they give you. This does not work after we get over 5 or so elements. And so I tried to do this and it worked through the debug input, but 5.2, the actual full input was not working. And I eventually realized, after trying to figure out why this wasn't working. I would run my solution, everything ends in like 40 milliseconds, and then this one like 10 minutes later wasn't even finished yet. And then I put in some debug statements and it was like, wait, we haven't even finished the first batch of ordering. So the first, page batches, we couldn't even get that in order in 10 minutes. And so like something was really wrong. So I looked back into this and I, remembered that this is actually close to n times m factorial, where m is like the number of pages in the batch. And this gets really big. And so I was like, well, how big is this? Like, why is this taking so long? Is my thing in an infinite loop or not? And I realized that the first input here was like 20 something elements. And I was like, well, how much is this? And it ends up being like super huge, which is like this really big number, which is like 2 quintillion or something like that. And even if we were doing like 1,000 calculations per second, we would take, a ton of seconds, or like 77,000 years or something. Like, my math is probably wrong. I was just like clicking these into Google, but basically confirmed that we do not want to do this at all. This is like super slow. This is like not going to work no matter if I, leave this running overnight or something. And so both of these did not work, the brute force solutions. So I had to look for something else. And basically it was like, okay, really what we're trying to do is we're trying to reorder our pages, and we get rules that are saying this stuff must come before this, so this stuff is less than this stuff, or this stuff is greater than this stuff. And then there's the possibility that we don't have any rules at all, in which case we don't know what order it needs to be in. And so if you actually think about it this way, like really what we're trying to do is just order these elements against each other, and we already have pretty efficient algorithms for sorting. And so if we could leverage those, then we could potentially order any out of order page in O of m log m. And so the idea here is that we pre-process the inputs so that we have both the, x comes before y, but also the y before x rules, so that we can compare in both directions, like a full kind of comparison based on what we understand about these elements. And then we use those rules in a custom comparer to determine the ordering. And so basically, if no set ordering, we would consider them equal, because I think it's possible that the values are missing here, but I'm pretty sure someone looked this up and actually all of the possible orders are in here. And so this comes a caveat of this approach. Like, this works if we have a stable ordering, but it is possible that the rules that they give you, the XY rules, might have cycles in them, or they might not be complete, in which case this could lead to an unstable sort and lead to like an infinite loop, or the .NET sort algorithm getting mad at you. Like, F# was crashing for this on me because I was doing compares that were returning the wrong values. But it does seem that Advent of Code is giving you the orderings without cycles and all, or at least all, necessary matches available. So just caveat on this if you're using this in IRL, but it does seem to work for Advent of Code. So anyway, after doing this, it looks like you can do this in n times m log m. So this is for, resorting the things, and is for going over all the elements, and then we need a little bit of extra memory because we're holding more stuff pre-processed of about 3n. And so here's all of the code, but we'll go into my editor as well. Okay, and so yeah, here's some artifacts of my poorly done solutions of trying to like, oh, we'll just randomize this stuff, or oh, let's find all permutations. And I was like, maybe permutations is wrong. Let me try this other one from Stack Overflow. But I don't think these were actually wrong. I think they just like were taking way too long to actually get anything useful. So finally, here's a code that I actually went with, and you can see that I've changed the input a little bit. One, I wanted to make sure that we had a set for these ints so that lookups were a little bit more ergonomic. And then I have the, x to y's, and then the y to x's. So all rules for things that must come after, and all rules for things that must come before. And then we still have our endless list of pages. And so basically the reading of the input is almost the same. We're still getting all xy pairs, but then we just, create two different dicts of x to y's and y's to x's. All pages is the same, and then we return this as structured input. This was my brute force one, which didn't work, and this is my new one. So let's just look at the actual solution itself to get kind of an understanding of how the flow goes, and then we'll dive into the page reordering part. So this is almost exactly the same as the original, right? So we get the input, we get our structured input out here. We, query our thing for is in order. We do create is page in order too, but it's basically the exact same. It just takes a dictionary then to set. And then we actually get the total here. And so this part's the same, right? We just look over all input pages. Then we choose the ones where they are not in order. And so this looks exactly the same, but here we're just saying if it is in order, then we don't care about it. But if it's not in order, then we do care about it. So we're choosing those. And then we're mapping over the invalid pages, and we're saying create valid from invalid page batches. And then again, we map over these. I'm just asserting they're in order, just for my own sanity. And then I pull out the middle elements, and then we sum those. And so here is really where the magic happens, create valid from invalid. And so for this, I'm just passing in the input because I wanted to grab a lot of things from this. And then I pass in the invalid pages that we actually want to process here. And basically what I'm using is I'm literally just using sort with, which allows you to sort, and this is like A, B, and then you just use your custom compare to return this. And so first off, we're saying, if x equals to y, then this is 0, they're equivalent. Remember that most of these sorts do like -1 if x is less than y, 0, and then 1 if x is greater than y. And so basically, first we need to check, is x before y? And I tried this with just looking at the number to values after it, but I realized that this was actually missing things and I was getting the wrong answer. And so I also needed to look at number to values before it. So both the x to y rules, but also the y to x rules. Basically, we're saying like, hey, if we have rules for x to things that come after it, if the thing that comes after it contains y, the thing we're comparing against, then this would mean that x must come before y. And then we do the opposite here where we just say, hey, if we have any rules for the number to values before it and y is in that, or for y, and then x is in that rule set, then we also know that x must come before y. And if that is true, then we're going to return -1 because x must come before y. Then we basically do the opposite thing here with y. So do we know that y actually needs to come before x? And so we look up the rules for number to values after it for y. If it contains x, then we know that is true. Or if we look at number to values before it for x and it contains y, then we also know that y must come before x, and then we return 1. Now, if we don't have this, then we can't actually determine this, and so we are returning a 0 as in their equivalent. Now again, caveat for this, like this does work for direct comparisons, but it does feel like if there's cycles or missing rules, you could confuse this stuff a bit, but it does seem to work for this input, so this is what we went for. Yep, that's it. All right, so next. So I enjoyed this problem a lot. I haven't run into a real life solution or situation in a while where the size of the input processing was like prohibitively large and expensive, or that the algorithm was like anything worse than like O(n squared or something, which for small n just like doesn't matter. And so this was a nice reminder that like it totally is worth doing the napkin math to make sure you're not doing some like n factorial calculations. I will say though that by the same token, n and n squared algorithms often lead to vastly simpler code, and for many data sizes it makes sense to bias towards simplicity over something that's optimal but like hard to maintain. So that's always the balance, but n factorial is another matter and would never like finish in my lifetime, so had to change that here. Now, if you like this post, please leave a like, comment, and share to your network for the algorithm so I know that we should make more of these. And you might also like some of these posts, Advent of Code 2024, my day 4 solution, why you should use snake case instead of camel case for variable names, and finally, how popular is F# in 2024. So that's it for this video. Thanks for watching, and I'll see you in the next one.